For example 2, determine the maximum and minimum points of f of x, so not just the values, we want the coordinates, using the second derivative test. Use these together with the concavity and the points of inflection to actually sketch out the curve. So, to start with, we have to determine the domain. When I take a look at this, I'm looking in that denominator. If I put in any number for x, if x squared plus 4 has to be greater than or equal to 0, well, that's always going to occur, no restriction. And because there's no number I could put in there that would make it equal to 0, the domain here is just x, e, r. For step 2, we're going to take the first derivative. So if f prime of x is equal to, well, hang on a second. Let's make this a little bit easier on ourselves. I'm going to rewrite that f of x. F of x is equal to 2 times x squared plus 4 to the negative 1/2. And now I'm going to derive that. Just using the chain rule. F prime of x is equal to, when I multiply it down, it's going to become coefficient of -1. X squared plus 4 all to the power of -3/2. And I'm going to multiply it by the derivative of the inside, which is going to be 2x, which means that f prime of x is going to equal -2x all over x squared plus 4 to the power of 3/2. I'm going to find my critical numbers. I'm going to pull from the numerator. And say that if -2x is equal to 0, then x would just equal 0. I'm going to pull from the denominator and say that if x squared plus 4 to the power of 3/2 is equal to 0, then x squared plus 4 would equal 0, and in this case there's no solution. Which means I only have the one critical number at x is equal to 0. All right, now we have to go and do our second derivative. So if our first derivative, f prime of x, is equal to -2x and x squared plus 4 to the power of -3/2, then we're going to say that our second derivative is going to equal -2x, and then the derivative of this using the chain rule, -3/2, x squared plus 4, now to the power of -5/2 times 2x, plus the second term, x squared plus 4 to the power of -3/2, and the derivative of -2x is just -2. This is going to give me, when I multiply it out, 6x squared times x squared plus 4 to the -5/2 minus 2 x squared plus 4 to the power of -3/2. I'm going to factor this, so I'm going to pull out a 2, and I'm going to pull out a x squared plus 4 to the power of -5/2, and that is going to leave me with 3x squared minus x squared plus 4 to the power of 1, which is going to give me 2 and 2x squared minus 4 all over x squared plus 4 to the power of 5 over 2, or the second derivative is equal to 4 x squared minus 2 all over x squared plus 4 to the power of 5 over 2. When I put in that critical number into this at 0, I get 4 times 0 squared minus 2 all over 0 squared plus 4 to the power of 5 over 2, which gives me negative 8 over 32, or negative 1 over 4. Using that derivatives test, what do we know? We know that when f prime of a number is equal to 0, and f double prime of the same number is, in this case, less than 0, and it's concave downwards, there is going to be a local maximum at x is equal to 0. So we've confirmed that there's a local maximum at 0, but we need to still pull the local maximum point. So if I know it occurs when x is equal to 0, then I'm going to say that if f of x is equal to 2 over the square root of x squared plus 4, then f of 0 is going to equal 2 over the square root of 0 squared plus 4, which is going to give me 1. So I know I have a local maximum point at 0 and 1. Now, we still need to deal with concavity, so we're still going to continue on using the second derivative to solve our significant numbers. So because we solved that the second derivative was equal to 4 x squared minus 2 all over x squared plus 4 to the power of 5 over 2, once again, I'm going to solve for my numerator and my denominator. So I'm going to do my numerator when 4x squared minus 2 is equal to 0. Then x squared minus 2 would equal 0, x squared would equal 2, and x is going to equal positive or negative root 2. When I take my denominator, for the x squared plus 4 to the power of 5 over 2, I find that there is no solution. There is no value once I isolate it and I get x squared is equal to -4. That would work, which means my significant numbers exist at positive and -2. So I'm going to check for when it is concave up and concave down. I have my significant numbers at -√2, at +√2. I'm going to pick some test points. Let's say -5, 0, and +5. And I'm going to see what happens for my second derivative, where I find that it is positive, it is negative, and then it is positive, which means that my function is going to go from concave up to concave down to concave up. And we see that there is a point of inflection at -√2 and at +√2. So I need to find what the coordinates are for those points of inflection. So I'm actually going to solve my f of -√2, or 2 over the square root of -√2 squared plus 4, which is going to be at 2 over √6, or when I rationalize that, √6 over 3. I can take f of +√2, which is going to give me 2 all over the square root of √2 squared plus 4, which once again will give me 2 over √6, or √6 over 3. Sorry, √6, not √3. So I have a point of inflection at -√2 and √6 over 3, and I have a point of inflection at √2 and √6 over 3. And then I'm going to piece it all together into my sketch. So I know I'm going to have a point of inflection at -√2 and √6 over 3. I'm going to have a point of inflection at +√2 and √6 over 3. I'm going to have a local maximum at the point of 0 and 1. I know in between these 2 points of inflection is going to be concave down. I know outside of these points of inflection is going to be concave up.